Welcome back. You still with us? Still with us there? Okay, good. So we're going to continue with part 2. If you don't already have your notebook, pen, pencil, whatever you want to write with is fine. Time to wake up, and let's continue. We still have a little bit more with a line, apparently. I didn't realize that. We have another question about a line. A line passes through the 2 points 4, 3, and -2, 5. Find the perimeter of the triangle. Okay, now we're getting into some applications here. The perimeter is just adding up all the side lengths, but we need to know what the side lengths are. So it's the perimeter of this triangle, which is bounded by this line and the coordinate axes. So let's just get a general idea of what that's going to look like. Of course, we're going to have the x-axis and y-axis as a boundary. This line is going to pass through the points -2, 5, 2, 3, 4, 5, and 4, 3, 3, 4, and up 3. Something like that. Okay, oops. So the triangle in question is going to be this triangle right here. Okay, we need the perimeter of that. So how could we figure this out? Well, we could easily use the y-intercept to indicate the distance of this, the length of this side. And then we can use the x-intercept, which is like way out there, to figure out this distance. And because this is going to create a right triangle, a perfect right triangle, we can then use the Pythag theorem, which is pretty much like the distance formula, if you think about it, with these 2 points here, the x-intercept and the y-intercept, not the 2 points that were given, but with the x-intercept and the y-intercept. Okay, so let's go ahead and do that. That means that we really don't need the equation of the line. You notice that? We just need to know what's the y-intercept, what's the x-intercept. I guess it will help for us to have the equation of the line. So let's go ahead and find that. The slope, if we want to call this P1 because the x is smaller and P2 because the x is bigger, that's fine. That's what I do, but you don't have to do it that way. You can switch them. We find the slope, which is y2 minus y1 over x2 minus x1. Be careful with that negative this time. That's -2 over 4 plus 2, which is a slope of -1 over 3. Now, in order to get the equation of the line, we're going to have to use this point, use this slope with one of the points in order to find the b value, which will automatically tell us our y-intercept, by the way. Let's just use this positive, right? Everything's positive there. So 3 equals -1/3 times 4, and then plus b. So 3 equals -4/3 plus b. 3 is just 9/3. So if we add 4/3 on the other side, we get 13/3 for the b. So this is the height of our triangle. We could just call it side A. I don't know. Maybe that's confusing to say b equals 13 over 3 and then a equals 13 over 3. Okay, we'll just call it b. Now the a value is going to be our x-intercept all the way out here. So let's set the y equal to 0 and say 0 equals -1/3 x plus 13 over 3. And that's pretty easy. That just means that x equals 13. So we have our base, which we'll call x equals 13. And now we'll find the length of this. Whoops, I tried to make a curly braces. I almost made a Gaussian curve. I almost made a bell curve. Okay, so this distance here is simply going to be the Pythag theorem. We're going to have 13 over 3 squared plus 13 squared, which is going to be 169 over 9 plus just 169. If we want to get that to be the same denominator, we do have to multiply it by 9 over 9. And we don't really have to worry about multiplying it. Why not? Because if we're doing 9 times this and 1 times this together, that makes 10 times 169. So we're going to have 1690 over the square root of 9, which is 3. 1690 isn't exactly a nice square root. It is approximately 41.1 over 3, approximately. But we can probably just leave it as square root of 1690. So the total perimeter of the triangle is going to be 13 plus 13 over 3 plus square root of 1690 over 3. And I guess if they really want you to simplify this, you can call it 13 root 10 over 3 plus 13 over 3. But that's just getting really down to the nitty-gritty. Either one of these is, I'm sure it's fine. Okay, so a little tougher. We have to think a little more for that one. Now, let's simplify. Oh, what do I tell you to look for when we're factoring is the greatest common factor. And you'll notice the top has a greatest common factor of 3. And that's going to leave us with x squared minus 10x plus 25. Very nice. This is just in the format of a perfect square trinomial. That's a perfect square. That's a perfect square. So this will be x minus 5 squared. And hey, doesn't that work out nicely because x minus 5 is also on the bottom. So that's going to cancel. And you can call it 3x minus 15. Or you can just call it 3 parentheses x minus 5. Either way is totally fine. We just needed to simplify, which meant to sort of reduce that denominator. Okay. Find all real solutions. Here we have some fractions. Fractions have rules. They have one rule, mostly. You cannot divide by 0. Do not have 0 in the denominator of the fraction. So let's just right off the bat say that x cannot equal 1, x cannot equal 2, and x cannot equal negative 1. So if after all of our work we get anything that suggests x equals 1 or 2 or negative 1, that is just eliminated. That's not possible. Now, how do we fix this? We have these kind of tough fractions to deal with. We can multiply everything, and I mean everything, all the fractions, each one of these 3 fractions, we can multiply them by the least common multiple, which would be x minus 1 times x minus 2 times x plus 1. It's like if you had fractions, guys. If you just had like 1 over 3 minus 2 over 7 plus 6 over 5, you would have to multiply them all by 3 times 7 times 5 to get the same denominator. So we're really doing the same thing here, but instead of having just single numbers in the denominator, we have variable expressions. So like x minus 1, x minus 2, x plus 1. And when you multiply that to each one of these things, now technically you're multiplying to the right side as well, but hey, that's easy because anything times 0 is just going to go to 0. Now on the right side, multiplying this into each term is always going to cancel with one of the factors. So the first one's going to cancel with x minus 1. That's going to leave us with 1 times x minus 2, x plus 1. Then we're going to subtract 2 times. On the second factor, the x minus 2's are going to cancel. So that's going to leave us with 2 times x minus 1, x plus 1. And then lastly, we have 6. This one is going to cancel with the x plus 1, and we would just be left with 6 times x minus 1, x minus 2. That equals 0. Now we're going to have to open this up a little bit. We're going to get x squared terms all over the place. So be very careful. This is a great opportunity to practice your foiling. Minus 2 times, you can work it all out. I'm actually going to complete this in pretty much like one step here. So minus 2x squared plus 2 plus 6x squared minus 18x plus 12 equals 0. And gather everyone together. Gather all the x squareds together. That's going to give us 5x squared. Gather all the x terms together. That's going to give us negative 19x And then gather all the constant terms together. Minus 2 plus 2 cancel. This is going to leave us plus 12 equals 0. And of course, we can try to factor this down. Let's try to factor it. 5 times 12 is 60. And then minus 19, that's going to give us two negative numbers. We're going to have negative 15 and negative 4. So let's go ahead and split this up with grouping. And remember, this is all equal to 0. We're just factoring this to make it a little easier. So let's use grouping. Group the first two. Group the second two. 5x times x minus 3. And then take out a negative 4 to leave the second group with x minus 3. So here we have 5x minus 4 times x minus 3 equals 0. Which means what? Which means x equals 4/5 and x equals 3. Those are our two solutions. And we can check and confirm that these are not any of the excluded numbers from the beginning. All right, there we go. Let's move on. This is similar but a little tougher, right? So in order to find the excluded values, first we need to know what makes these things 0. So we're going to need a factor. We're going to need a factor anyway to figure out what the common denominator is. So let's go ahead and do that. This is going to be, what is this going to factor to? X minus 16 and x plus 3. So this tells me that x cannot equal 16 and x cannot equal negative 3. Let's move on to factor this one. This is going to be x minus 16, x minus 2. So we already have that x cannot be 16, but now x cannot be positive 2. And then lastly, we have x plus 3, x minus 2. So we don't get any new restricted values there. That does mean that our common multiple is going to be x minus 16, x plus 3, x minus 2. And that's what we're going to multiply to both sides. All of the terms, all three of those terms, we're going to multiply that to both sides. And when we do that, it's kind of nice because two of the factors are going to cancel. And so really, we're just going to have the first fraction be 4 times x minus 2. That's the only one that's left. For the second fraction, the x minus 16 and the x minus 2 are going to cancel. So that's going to leave us with just negative 2 times x plus 3. And this is going to be equal on the right side to 1 times x minus 16. So we still have to work some stuff out, but it's a lot easier. We don't have a quadratic that we need to factor again. Just make sure that, you distribute carefully, like I almost did not. And you get everything to one side, all the x stuff on one side. Let's move it all to the left. So subtract x, that's negative 3x with the 4x, that's negative 3x plus 4 is 1. And then move all this number stuff to the other side. So plus 8, plus 6, which is plus 14. X equals negative 2. Was that excluded? No, I think positive 2 is excluded. So this is valid solution, but you do want to check every time. Make sure you're not getting something that's going to cause a 0 in the denominator of a fraction. All right, let's keep it cranking. Here we have a situation where not everything's in a fraction, but we do have some fractions, and so we need to restrict. X cannot equal negative 1 because of this one, and x cannot equal positive 1 because of this one. So we're going to have to multiply by x minus 1 times x plus 1. All right, that's going to be our common multiple. And we're going to have to multiply all three of these terms to it. So the first one, we're even going to have to multiply the 2, and we're going to have to multiply this one here. So when we distribute to the first term, the x plus 1's cancel. That's just 4 times x minus 1. The 2 doesn't have anything to cancel, so it's going to take both of these, x plus 1 times x minus 1, and then equals 15. The x minus 1's now are going to cancel. So it's just 15 times x plus 1. Okay, so let's work this out. We get 4x minus 4. Work on your FOIL here. This is going to be 2x squared minus 2. And then we have equals 15x plus 15. So let's get all the terms on one side. This is clearly quadratic because the highest power that we have is that 2. And so let's move everything over to the left side here. We're going to end up with 2x squared. If we subtract this 15x onto the other side, we're going to end up with minus 11x. And if we subtract 15 on the other side, we're going to end up with negative 6 and negative 15, which is negative 21. All right, let's see. Can this be factored? Yes, I believe it can. Let's take a look at what it would be if we multiply to make a negative 42, but we combine together to make negative 11. That means a big negative and a small positive. How about 14 and 3? That way we're going to have 2x squared minus 14x, and then we're going to have positive 3x minus 21. Notice how I said them kind of separately in groups because we're going to group factor them. Take a 2x out, leaving you with x minus 7, and take a 3 out, positive 3 that is, leaving you also with x minus 7. And the final factored form, that sounds nice, final factored form, before we solve is 2x plus 3 times x minus 7. And these values were not restricted, only plus and minus 1 were restricted, so these are valid solutions. These are all the real solutions. Okay, great. Here's something called direct solving, or sometimes we call them literal equations because we are literally just solving for x. We want to get the x by itself. And there are a couple of ways to do that. First, we have to notice that this is quadratic. Otherwise, you're kind of going to struggle a lot. If you're trying to just get x terms on one side only and then factor, it's going to be tough. You'd be better off moving this x squared thing on the other side so that it's positive. Minus 3px plus 1. So here's kind of what we can do. What we can do, I'm noticing, is that we can group the p and the x together and call it a. So we're going to call p times x a. So that this is basically 2a squared minus 3a plus 1. And then we can sort of break that down and factor it. Equals 0, of course. That's what we did. We removed everything from the right side, so it's 0. We find two numbers that multiply to 2 and combine to negative 3. That's going to be negative 2 and negative 1. Therefore, 2a squared minus 2a minus a plus 1 equals 0. Do a little group factoring from that first group, and then take a negative 1 out from that second group, and you end up with 2a minus 1 times a minus 1 equals 0. Now remember, and we can even go a little further, we can solve each of these. We can say that a equals 1/2 and a equals 1. Remember that a is actually p times x. So now all we have to do is divide both sides by p, and so we get x equals 1 over 2p and x equals 1 over p. Those are solutions. And how do you check those solutions? If you were to plug them into the original equation, like 1 minus 3p times 1 over 2p should be equal to negative 2p squared times 1 over 2p squared. That's how you would check one of them. How would you check the other one? You would plug this in. 1 minus 3p times 1 over p equals negative 2p squared times 1 over p squared. So just check that those are true on the left and the right side, that they're equal, and you will verify the equation. Okay, solve for x in terms of the other letters. Look at this. These literal equations are getting more complicated. So we're looking for x here. And this isn't too bad. There are several different methods here. If you want to get the same denominator, that's a great method. Multiply by a on top and bottom of this fraction. So now we have ab plus 3 equals ax. Sorry, ab plus 3 over ax equals b. I mean, there's several things we can do here. What would I do? I would probably multiply ax on both sides to get ab plus 3 equals abx, and then you can divide both sides now by ab. So see what we did there is we kind of brought the ax over, but we're just going to send the ab back because all we want is x. So x equals a times b plus 3, all of that over ab, and therefore if you like, you can simplify this as, breaking up the numerator of a fraction. So we can just call this 1 plus 3 over ab. If you'd like, that's just simplifying some stuff a bit extra. Do you have to do that every time? No, but if you can do that, I can guarantee that you're at a higher level of understanding. So take that as you will. Here we go again. Solve for x in terms of the other variables, the other letters. So here we have x on this term, x on this term, x on this term, x on this term, but this is a squared. Okay? So we're going to have to be a little bit careful with this because this is a squared. What I want you to realize is that these terms here, these are all on the same level, the same degree. For example, this is a times x. This other one is 1 over 3b times x. And as soon as I add this over, this is it's positive r times x. See how they're all just times x? So they're all pretty much the same kind of term. They just have weird coefficients. Imagine this is like 3x, and this is 2x, and this is 5x or something. But they're all x terms. So they do all go together. All right, is that clear? That being said, what I probably want to do is move some of the stuff from the left over to the right side, honestly. I think I would rather move stuff over to the side where the x squared term is positive. So here we go. We have 0 equals 4x squared plus, or maybe I should say minus all of these coefficients. We have a plus 1 over 3b plus r, all of that times x. So what can we do here? We can factor out x. So this is x times 4x minus a plus 1 over 3b plus r. Yeah, that looks about right. And if we want to set each of these equal to 0, okay, we get x equals 0. For this one, we would have to do a little work. If this is equal to 0, that means 4x is equal to, that should be in parentheses. It should be 4x equals a plus 1 over 3b plus r. So that just means x equals all of that stuff. I'm not going to worry about getting the fractions to look nice. I don't mind that there's a fraction on top of a fraction over 4. And x equals 0. That's also a solution. A less complicated solution. This one's a little more complicated of a solution. All right, let's keep it going. Speaking of fractions on fractions on fractions, we got some complex fractions. So let's fix this up a little bit. Let's deal with the top first. Let's make the top compatible so that they can add. We're going to need to multiply this by x over x. So this is going to be 9x plus 3 over x. And then let's simplify this one. We really just need to multiply by a 3 and multiply by a 3. So that's going to give us 3x over 12 plus 1 over 12, which is the same as 3x plus 1 over 12. And since this is a fraction divided by a fraction, how do we do that? We flip the bottom fraction and multiply. So this would be 12 over 3x plus 1. And it might seem like nothing really cancels there, but actually something does cancel there. We can factor out the 3 from the top of that fraction, and it's going to cancel really nicely with the 3x plus 1 now that we have in the denominator. So we end up with just 3 times 12, or 36 over x. Interesting. Yeah. Okay, let's take a look at this next page here. This we simply want to simplify. We just want to simplify. We don't want to solve anything, but we're trying to add some stuff that involves fractions, and we definitely do not have the same denominator. Let's factor this down. A good guess is that x plus 1 will be a factor, but not necessarily. However, let's try it as a possible factor. That would work out really nicely with x plus 3. So now to combine everything, we would have to multiply this 1 by x plus 1, x plus 3 on top and bottom. And for the first fraction, we would only have to multiply the top and bottom by x plus 3. X plus 3, x plus 3. And go ahead and work all of that out. I will be wasting no time in writing all of this out. X squared plus 5x plus 6 plus 4. Careful with this. Minus the quantity x squared plus 4x plus 3. And of course, this is all over x plus 1 times x plus 3, which I guess I'll leave it like that for now. Let's work some of this stuff out. X squared minus x squared. That's nice. 5x minus 4x. That's going to be 1x. 6 and 4 is 10. Minus 3 is positive 7. And so we end up with x plus 7 over x plus 1, x plus 3. See how easy that was? So we really are just following basic principles here. We're trying to get the common denominator so that we can add all this stuff together. Okay, find all real solutions. This is a quadratic, clearly. The highest power here is 2. Let's get this 15 moved over. And we don't have any greatest common factors, so we're just going to jump pretty much straight into some, what's this, x game factoring. 8 times 15, that's going to be 120. And they need to combine to be negative 19. Okay, so my first thought was off. I was thinking about, oh, no. What I was off with is not subtracting the 15 on the other side. Remember, this is minus 15. So this is minus 120. Okay, good. My numbers work then. Negative 24 times 5 is negative 120, and negative 24 plus 5 is negative 19. So let's split the middle. Instead of calling it negative 19x, let's call it negative 24x. Plus 5x equals 0. And now we can do some group factoring in order to solve. 8x times what's left, x minus 3, plus we're going to have to take a 5 out to also leave x minus 3. And we'll have 8x plus 5 times x minus 3 equals to 0. And those solutions will be x equals 3, of course, and x equals negative 5 on 8. Bam. Those are real numbers, so we're good to go. Find all real solutions here. Well, let's see if this factors. I don't suspect that it does, but do we have two numbers that multiply to negative 3 and combine together to negative 1? Not nice numbers, so we'll have to bust out the old quadratic formula. Our b value is negative 1. Be careful of that. Negative b means negative 1. B squared minus 4 times 3 times negative 1 Okay, that guarantees I have a positive inside all over 2 times a. So this is going to leave me with 1, like positive 1, plus or minus square root of 1 squared is 1, 4 times 3 times 1, that's 12. Hopefully all that curly drawing made sense. I don't know why I did that. Over 2 times 3, which is 6. So we get two answers. We get 1 plus root 13 all over 6, and we get 1 minus root 13 all over 6. You'd be shocked. I bet if I showed like 75% of adults who are not in like a STEM field specifically a quadratic equation and told them like find the x numbers that make this equation true, they would sit there forever just trying whole numbers. Maybe they would try fractions. If they don't remember the quadratic formula, they're honestly, you're fucked. that's the only way. Imagine like 400 years ago, it was very common to not know this and it was okay. But nowadays it's like, bro, I can give you a basic little equation that a 14-year-old can do. Come on. All right, find all real solutions. Now this looks sort of quadratic. I see a squared, but it's not the highest power. The highest power is 4. However, if I sort of evolve a typical quadratic equation, if I think about like this and number, if I sort of level up this by squaring it and squaring it, I would get x to the 4th. So that leads me to a substitution. I'm going to replace x squared with a. And by doing that, now I have a quadratic equation with a. A squared minus 4a minus 32 equals 0. And this very easily factors to a minus 8 and a plus 4, which means a equals 8 and a equals negative 4. But remember, a stood for something. It stood for x squared. So x squared equals 8 and x squared equals negative 4. This one has no real solutions. It does have solutions. It just doesn't have any real number solutions. It only has I solutions. So the solutions of this would only be, let me draw those squigglies a little better, would be negative 2i and positive 2i. Those would be your imaginary solutions, not including those. But for here, we would have plus or minus square root of 8, which is 2 root 2, and negative 2 root 2. Those are the real solutions. That's why sometimes they specify find the real solutions, or they might say find all solutions. Okay, definitely a breath of fresh air here. Goodness, this is easy. So it's possible that the inside is just literally equal to 4. And so when you put that in the absolute value, it doesn't do anything because the absolute value of 4 is 4. But it's also possible that the inside is equal to negative 4 and it gets switched by the absolute value sign. So we need to consider both of those possibilities. So x could be 11 over 2, or x could be 3 over 2. Yeah, breath of fresh air indeed. That was probably the easiest one on the whole packet. Okay, let's take a look at this slightly more complicated expression, but it's not that much tougher. In fact, I think we did a tougher version in part 1 with the inequality. This one is much easier. We want to simplify the middle first. So let's multiply the top and bottom by 4, and let's multiply this top and bottom by 5, and we end up with 4x plus 1. Sorry, 4x plus 4 minus 5x minus negative 5 all over 20. And so this just turns into negative x plus 9 over 20. So it's possible that this thing inside, negative x plus 9 over 20, it's possible that the thing in there just equals 1. And so it didn't have to change because it was already equal to positive 1. Which would mean that negative x plus 9 equals 20, which would mean that negative x equals 11, or in other words, x equals negative 11. But it is also possible that the inside got switched to positive 1, which meant it was really equal to negative 1. So let's go ahead and check that. Negative x plus 9 equals negative 20, which means negative x equals negative 29, or just x equals 29, which seem like some tough numbers to work with here. How do we know that they work out so nicely? Do they work out so nicely? Well, you can check them. Let's check them. Let's try negative 11. That's negative 11 plus 1 over 5. That's a nice number. Minus x minus 1. So negative 11 minus 1 over 4. Well, that's going to give me negative 10 over 5 minus negative 12 over 4. So that's negative 2 minus negative 3, which just equals negative 2 plus 3, or 1. Yeah, that works out. I trust that 29 works out as well. I have no reason to think that it doesn't work out. All right, let's take a look. Compute the quotient. So you see that there's a square root in the bottom. How do we really divide these things? You don't have to bust out the long division and start calculating like if I were trying to divide 3957 divided by, 13 or something. You wouldn't have to worry about that. The way that we divide these is we use conjugate multiplication. You might have seen that earlier. I think it was like number 14 or something from part 1, where we had to do conjugate multiplication, because a conjugate multiplication is going to guarantee we get a difference of squares, and squares break square roots. So let's multiply by the conjugate. The conjugate of the bottom is 1 minus I root 3, kind of like the evil twin. And on the top, that's the same thing that's already there, but we have to multiply the same on top and bottom because we're multiplying by a number divided by itself, or in other words, 1. Okay, in the top, let's work that out a little bit. So 1 times 1, 1. 1 times minus I root 3, and then we're doing that twice, is minus 2I root 3. And then minus I root 3 times minus I root 3 is positive I squared times root 3 squared, which is times 3, all over this difference of squares. 1 squared, 1. Minus I squared times 3. Remember that I squared is equal to negative 1. So this is just equal to negative 3. So we have 1 minus 3. That's negative 2 minus 2I root 3. And on the bottom, this just becomes 1. Let's see, that's a negative 3, so this is a positive 3. Okay, 1 plus 3. And now we're cooking. Now we're getting somewhere. There we go. Divide both by 2. And that's the most that we can reduce. If you want to put it in fancy format, you can have it like, I call it fancy format, because some people get very picky about separating those two, the real part and the imaginary part. That's fine. People are going to get up in arms about it. Okay, same kind of process. 48. This is a great opportunity for you to try yourself. If you can do this, if you know what to multiply, and if you've taken that moment, all right, let's proceed. We're going to multiply top and bottom by the conjugate, which in this case is 5 minus 2I on top and bottom. So you got to be good with FOIL multiplication. You got to be really quick with it, but very accurate. So we're going to have 15, negative 6I, and negative 10I makes negative 16I. Then we're going to get positive 4I squared over 25 minus 4I squared. Remembering that I squared is a negative 1, so this is really 15 minus 4, or 11. And on the bottom, this is really negative 1, so this is 25 plus 4, or 29. And that is as much as we would reduce that one. They don't have any common factors, so we don't need to reduce that anymore. Okay, let's take a look at these radical expressions. Now, all of these have a negative in it, which means they're the same thing as this with no negative in it, but then times I. And it's very important that the I is not in the square root. I is just a tag. It's just a label that goes on any square roots which have a negative inside. Plus square root of 80 I. So putting these together and combining them as like terms is the same process as when we're dealing with square roots of positive numbers. Let's break this down and get as much of perfect squares as we can out of there. Okay, so we have 2 times root 5 I. This is going to turn into root 9 and root 5. So we're going to have 3 times 3 from the square root of 9, root 5 times I. And then what can we take out of this? We can take 16 in a root out of there. So this is going to be plus 4 times root 5 times I. So putting this all together, we basically just have 2 plus 3 times 3, that's 9, plus 4. 2 plus 9 plus 4, that's 15 root 5I. Pretty easy stuff. We're just simplifying radicals at this point. Okay, let's take a look at number 50. This will make almost a halfway mark. Negative 4 plus 5I squared. Well, that's simply going to be negative 4 plus 5I times negative 4 plus 5I. Sometimes it helps students to write this out like this. If it helps you, go ahead and do it. If you don't need it, don't do it. It's a waste of time if you don't need it, but if you do need it, it's very much not a waste of time. So don't feel bad either way. I trust you to FOIL properly. This is some basics. 25I squared here. Remembering that I squared is negative 1, so this is really 16 minus 25, which is a minus 9, minus 40I. This is the overall value, because we switched the I squared into negative 1. Okay, let's get a couple done in this sort of quote-unquote second half of problems. I know there are plenty, so let's give it a full run-through. Scrolling through the void. Yes. So we're going to simplify powers of I to the 95 power. Well, that's quite weird. Let's think about it like this. We know that I squared equals negative 1. So we know that I to the 4th equals positive 1, because I squared times I squared is just negative 1 times negative 1. That's positive 1. So if I have any power of 4, like I to the 8, that's just I to the 4th and then squared. So basically, if we have any multiple of 4, that's what it's going to be. It's going to equal 1. So like I to the 12th, I to the 16th, I to the 20th. You get it? So I can jump by groups of 20 now. So that means even I to the 80th is going to be equal to 1. And even I to the 84 is going to be equal to 1. You get it? If I keep going, I mean, I don't have to even go that far at this point. I'm pretty close to the end. If I keep going, I have I to the 88, which is also equal to I to the 92. Okay, what do we have here? We have 95. So the trick here is to divide as many, or rather to subtract as many multiples of 4 as you can. So that means that I-95, that's funny, that is a pretty popular freeway, I think, is going to be equal to I-92 times I squared times I to the 1, right? All of those add up together to 95. Why do I do that? Because this is simply 1, this is simply negative 1, and I mean, this is simply I. So our result after all of that consideration is just negative I. Yeah, there's sort of a pattern, a cycle of I here. Whoa, simplify I to the 2010 power. Well, any power that is a multiple of 4, like 2000, is going to equal to 1. So we can sort of jump ahead by 2000 powers, and we can look at I to the 2004 is also 1. And then we can look at I to the 2008 is also 1. Now, to get to I 2010, you just have to multiply I squared. So this is going to be I 2008 times I squared, which is just going to be 1 times negative 1, which is just negative 1. Very simple here. Okay, let's finish up this segment, this part, with this final work on some imaginary radicals. Just remember that this is the same as square root of 30. Whoa. Square root of 30 times I. And this is the same thing as square root of 3 times I. So is there anything that we can do here? Oh, we're multiplying, not adding them. Got it. So we can multiply these together, and we can make it square root of 90 I squared, which this can break up into square root of 9 square root of 10, which gives us 3 square root of 10 times I squared, remembering that I squared is negative 1, so this is negative 3 square root of 10. Very interesting. Okay, that should do it for the second leg of the marathon. Hope you're hanging in there. This was kind of the easier leg, I'm not going to lie. The second leg is going to be, the third leg is going to be more challenging, and of course the fourth leg is going to be a little bit brutal, but hang in there. I know you got this.